Welcome to today's seminar. It gives me great pleasure to introduce today's speaker, Professor Ved Chirayath. Right. Let me give an introduction. Ved, right? He's oh my God. Technical issue. Ved's received his PhD in 2016, so relatively recently by my standards, for sure. But he already had quite a remarkable career. Starting from being a sophomore in high school, when he invented a new sensor for a telescope, right, and discovered a new planet. That piece of information made me upset as a parent. I wish my kids. Anyways, so he received a bachelor degree from Moscow State University, same school my wife went to a little earlier, right? So he speaks Russian. So I should be careful around him. And at least he's the only person who understands what I'm saying in this school anyway. So he got then he received a second bachelor degree from Stanford, right? And a master's degree from Stanford in aeronautics. And a PhD from Stanford University, working in the same field. He had a long list of awards and achievements, inventions, patents, publications. For many years he directed a center at NASA, being a civil servant. And then he moved to Rosenstiel, to Miami, and he's associate professor in our Department of Ocean Sciences. So he will talk today about his exciting research, flying boats and drones. Today's seminar serves a dual purpose. That is also being considered for a promotion. So this seminar is also part of the process. So the stage is yours, please.
I appreciate it. Thank you, Igor and Roland, for helping set this up. I'm excited to see you all. I'm fresh off of vessels in California with whales. It was extraordinary. My student Cam and I got to spend an entire week with them and some of our Stanford collaborators. And now I'm all about the charismatic megafauna, but I will today focus on the majority of my work, which is on developing new sensor technologies for studying the ocean. And as Igor mentioned, this is a bit of a dual purpose role, but I will try to keep the promotion justification portion short. So I'm just here upstairs. I direct the Aircraft Center for Earth Studies. I was directing the Laboratory for Advanced Sensing at NASA ACES for 10 years before coming here 2 years ago. And the center has grown. Most of our lab space is up here, and we have a drone center that is opening up in North Grosvenor. It's just been refurbished, and we'll be soliciting multiple hires to fill those roles and build aircraft at the center. So just to give you a little bit of background of who I am, I grew up in LA with like a menagerie of rescued animals, including rats and dogs. I was really interested in life, in astronomy, and the ocean. Southern California kind of had all of these, although the water is a little bit colder than it is here. For my entire career, I've really been driven by one question, and that is, are we alone in the universe, and what is so special about life, if Earth is the only example we know of right now? This is an area of the sky about a quarter the size of the moon. It's relatively dark in the night sky, and Hubble stared at it before this image for about 30 days, and then when it took this image, another 20 days to resolve galaxies teeming everywhere in the scene. It looks pretty dark. The only thing in this image in our galaxy is this star. So every single thing you see is another galaxy, which gives you an idea of just how much is out there. So I naturally wanted to work at NASA. I wanted to explore the cosmos and try to find objects. In high school, this overlapped with me being homeless for about 3 years, so I ended up living on top of a mountain, developing telescopes and looking for planets. That resulted in a successful detection of a planet when I was a sophomore, and then that kind of launched my career in astrophysics and theoretical physics. I did my degrees in Russia, went to Stanford for my advanced degrees, and then got hired immediately at NASA AIMS just down the road in Silicon Valley and directed this lab here in sustainability base, focusing on developing instruments for studying the cosmos. And around this time I realized a lot of things about space. One is I really wanted to go there, still do. So I was lucky enough to be one of the 30 finalists for the class of 2021 astronaut class. But this drive to go to space was really motivated, again, by looking for life. And I'm trying to understand, where else is it? What makes it so unique? And in the back of my mind, I kept thinking of that passion I had as a kid for the ocean, right? And I was watching this amazing biosphere changing on timescales that I did not expect to happen in my lifetime. So I decided to do something about it. I pivoted from astrophysics into oceanography, and now I'm sort of a practicing astrophysicist in oceanography. In 2023, this still holds true, no matter how many times I show this slide. We've mapped about 5% of our seafloor to the same resolution as we have of the sun, the moon, those are both my images, and Mars. So we know more about objects that are many, many, many AUs away, astronomical units, from our home planet than we do about our seafloor. We lose things the size of jet planes with hundreds of souls on board, and we still cannot find them on our seafloor. By comparison, on Mars, we lost a rover the size of a golf cart. It took about 6 days to image that crash site and to know exactly where that golf cart-sized object went down on a body away from Earth. So just let that sink into your mind about the technical disparity that exists between aerospace, astrophysics, and oceanography. I'm also very excited about oceans because as someone who's looking for life, we now have hit the celestial jackpot. We have multiple ocean worlds in our backyard. These are moons of Saturn and Jupiter. Some of my favorites are Europa up here. This is a moon of Jupiter that's got ice cracks with organic material coming up. Enceladus, which has got cryovolcanoes, so these are ice-spewing volcanoes that are populating now what we think are Saturn's rings with ice crystals. Triton, a moon of Neptune, looks like a captured Kuiper belt object, very similar to Pluto or Charon. And then Titan, not to disappoint, if you look in the infrared, Titan reflects sunlight off of its methane and hydrocarbon oceans and its lakes. So when you're looking for life on our home world and you think, where's the best place to go? 99% of the habitable volume of our planet is in the ocean. When you look elsewhere in the cosmos, we've sort of been blinded by our terrestrial origins as monkeys, right? We think life should be land-based, you need liquid water, but maybe that's not the case galactically, right? Perhaps if you follow the water, really what you should be doing is looking for oceans. And we now think Europa has an ocean that's larger than Earth's oceans underneath its ice sheet, and it would be protected from radiation, it would have hydrothermal heating. So these are all prime candidates for life searching and detection, but to get to any of those worlds and explore them, you first have to figure out how to do it on Earth, right? How do you get into those oceans and not die? How do you get your robot into those oceans and not die? Everything dies in the ocean, I think. So what I'm trying to motivate in my field is, the Hubble Space Telescope moment for oceanography, I think, came and went. We need a Webb Space Telescope moment, right? If astronomers can convince Congress to fund a $14 billion space observatory that lives at the Lagrangian point that no one sees or touches, we can fund a $7 billion ocean observatory that's dedicated to observing and protecting life as we know it. So with that aim, I moved here with my NASA team, largely, and founded the Aircraft Center for Earth Studies. You can see some of my team members here. In fact, they're in the audience. My student Jesse, Heidi, who just transitioned to NOAA, Anna Toronto, Cam, who just came back from the whales, so he's probably resting. Who else do we have in there? And Noah, who's up at Cornell at this moment. ACES focuses on 4 core areas, mostly sensor development, and I'll talk today about FluidCam and MIDAR and the latest updates since I've gotten here on those technologies. Aeronautics platforms, typically your sensor is only as good as the platform you were flying it on or you were driving it on. So a lot of time and energy goes into advancing robotic systems, using the helicopter platform for its heavy lift capabilities as well as other airborne platforms. The third component is an AI component, which Anna is currently leading as our senior data scientist. This is what you do with all the data coming from these sensors. And then the fourth, which I'll be starting up soon, is a CubeSat program where we will start building satellites here at Rosenstiel and launching those payloads into orbit and getting student opportunities to fly into suborbit. All right, so what are some of the fluid lensing developments that we've had since I've got here? So this is a site in Guam called Tumon Bay that my team and I have been visiting for the last decade or so. It's a very nice coral reef where a lot of tourist activity occurs. And you'll see a couple issues with looking through water from space. One is that it's very dark. not unlike when you look at the night sky. And this is why it's so easy for me to be an astronomer in oceanography, because the amount of light you deal with in space, where you're looking at very, very few photons from the origin of time, is very similar to like looking at the ocean past 100 meters depth, right? Most of the photons are absorbed, scattered, attenuated, absorbed by plankton. So in our Earth's atmosphere, we have a window that light penetrates in the radio. Unsurprisingly, all of your telecommunication systems, GPS, radio observatories, they all work in that big radio window gap. A lot of radars also operate there. Unfortunately, in water, everything to the right of red, so basically red to infrared, near infrared, microwave, all of that gets absorbed within the first micron of the surface of the ocean, which means your cell phone does not work underwater, your GPS does not work underwater. Basically, nothing much works underwater. Similarly, on the left-hand side, after ultraviolet, as you get shorter in wavelength, all the way down to X-rays, gamma rays, those also get highly absorbed and attenuated by water. There actually is a little window in X-ray which you can get scanned with, but we don't use X-rays to study the ocean. So, by and large, the first issue with trying to study the ocean is it's dark, you have attenuation. As you get deeper in the column, you only see certain colors of light, usually blue and ultraviolet, and it's also very little amount of light that gets reflected out. The second issue is something you learn about very early on. Light travels at different speeds in different media. So when light crosses the ocean-air interface, it gets bent, and that means that when you're looking at something underwater from your eyes or an aircraft or a spacecraft, it does not actually appear to be where you think it is, right? You have to know the fluid you're looking at to make a correction to predict where that object is. Now, some fish can actually do this in their heads. Triggerfish can shoot a little thing out and eat a bug that's floating on a branch above the water. Humans aren't really good at this, actually. They keep trying to hit fish, and the fish is completely in a different location. If you add ocean waves to the mix, it gets really difficult, because now you have distortions that will blur the image that you're looking at. And right now, none of our satellite systems or aircraft systems can see through that. So if you have a satellite that's capable of seeing at the 10 centimeter scale on land, the minute you get into water, it's no longer the case. In fact, it might be as bad as 5 meters to 10 meters, and don't try positioning that object reliably, because, again, you have refraction. So unless that's been accounted for, the apparent location of that object might move. This is why there's not really a Google Earth for the ocean yet. Okay, so I set out to study this phenomena in my PhD, and then this became a NASA instrument. This is a supercomputer simulation of this phenomenon I call fluid lensing, where fluids interact with light. You'll notice a couple interesting features as you get deeper in this synthetic pool. This is about 5 meters depth. Waves will periodically magnify and demagnify an object if you look at it in slow motion. You'll also see the effect of waves focusing sunlight down into these bright bands of light called caustics. So I sought out to create a sensing system that exploited that positive magnification effect of waves to see at very high resolution, and to also exploit those caustic bands to see very deep in the water column. They essentially give you a torch that lights up the object, and it can be 100 times the intensity of sunlight at the sea surface. So next time you go diving, wear your sunscreen, because you are being zapped by little, well, not little, large magnifying lenses on the surface of the ocean that are just focusing sunlight down into poor little you. This also explains why you get sunburn if you only dive all day and you never really see the sun above the surface. Okay, so that was synthetic. Now I tried to create this technology and deploy it in the real world on drones. So I did a lot of foundational work in American Samoa. This is from American Samoa in 2016. And here you can see a fringing coral reef. And this is the view you typically get from the sensor. So you have a lot of reflection on top of glare and refraction and absorption. And this is the fluid lensing view of that same environment. So the technology is capable of tracking those magnification events and the caustics to see both at higher depth in more colors, as well as seeing things at higher resolution. So now we can resolve things like a cropper coral, Chirayath coral, corals that typically need a sub-centimeter level of precision to assess their species type, and we can do that at scale from the air. Okay, so this is all stuff you've seen before. What has changed since 2022 and 2023? Well, we revisited Guam, and one of my collaborators there, who keeps pushing me to think of new ways of imaging, says, well, what about all of this breaking wave nonsense? How do you get through that? And I said, it's impossible, don't bother. Let's just image everything in front of it and behind it. Some more cajoling and thinking encouraged me to figure out how to resolve that. And now we can actually successfully see-through breaking waves in a world first. So these are contemporaneous satellite images and fluid lensing images from that same region. And a ton of areas are actually uncovered that only exist in that surf region, which is kind of interesting from an ecological standpoint. In this particular example, there's a new type of coral species that again exists only along that surf line, and you can only see with fluid lensing. So right now the method is working very similarly to a telescope. It's integrating photons over time and counting them, which allows me to basically remove the effects of dynamic waves or wave breaking. So as long as there is a 1 in a million chance that a little photon makes it out through a wave break, and there's still some artifacts you can see here remaining, we can resolve what's underneath it, and we can also do that in 3 dimensions. So this is a full 3D image of Tumon Bay at the sub-centimeter scale, and it gives you an idea of, truly how much you can cover in one area, and also gives rise to precision coral resilience-based management practices. So now when practitioners go out there and want to track the change in a particular species or type over time, they can use geo-reference data sets to actually get them there and show them what it looks like. In Guam, we worked very closely with the governor and lieutenant governor. That's my student Stephanie, who recently graduated. And the program there has really taken off. We've trained 25 local pilots per year. They're flying their own drones now. We've sort of transitioned to a capacity building model where we don't have to always come in and be the parachute scientists. They can do a lot of the work themselves. And as a result, more and more coral gets mapped at a higher frequency than we've ever thought possible. And we're living in this golden age of tons and tons of data. More recently, we've been branching out in Florida. We've secured multiple NOAA grants to look at changes in coral cover in the Keys as part of Mission Iconic Reefs, which is an ambitious coral restoration effort. This summer, of course, there was a marine heat wave that affected almost all of the reefs there. You can actually see here the bleaching event we did right after we came back from the Pacific. We deployed on an emergency mission to capture the bleaching of multiple corals that we had just surveyed. This is just out of Horseshoe Reef, which is about 15 miles south of our Broad Key Research Station. So the technology is working now very well. We're trying to just expand the footprint as quickly as possible to get conservationists the tools they need to assess what they're looking at. Some other developments my students have been hard at work on are trying to assess biomass in addition to the coral benthic diversity that we see from fluid lensing data sets. Typically, fluid lensing would delete everything in the column that moves as a function of the wave. So that literally meant every fish, sea cucumbers would resolve, sea stars, things that are sessile would resolve. But other things, sharks, sea turtles would get deleted. We're now going back to that raw data and actually trying to suss out, once we know what the benthic surface looks like, pulling out what some of the wave distortions and just isolating what creatures live there. And that allows us to, in the case of sharks and sea turtles, pretty reliably do a count, body size, morphology, and try to get to biomass metrics, which is an essential part of assessing the health of really any ecosystem. Okay, so now you might be in your head thinking, how do you take these data sets, which are sub-centimeter scale, 3D, and extract meaningful information from them at island scale? So when we do a mission in Guam, we're talking about each mission being 150 terabytes of data. A good high-quality laptop is probably about 1 terabyte of data. NASA's entire Landsat program per annum produces around 300 terabytes of data. We produce north of a petabyte per year. So all that data has to be churned and used somehow, otherwise it's just costs money. Does it actually produce science? And so for that, we actually created a project called NEMONet, launched in 2020. And this is now led mostly by Dr. Anna Tirano, who's extracting coral reef metrics directly from the data sets with citizen scientists helping. So I'll play a short video on how NEMONet works.
NASA NEMONet is a game where you classify the world's coral reefs by painting on real-life images scanned from the ocean floor using a revolutionary instrument that lets us see beneath the waves at unprecedented resolutions. Our oceans are so vast, it would take us 2 million years to classify the world's coral reefs by hand. The classifications you create are sent to our teams of NASA scientists at home base to teach our supercomputer to classify coral reefs on a global scale. Every contribution you make brings us closer to solving this problem. Join the NASA team to help us understand these amazing ecosystems. Take command of your research vessel and learn about all the different types of coral. We must keep the ocean alive. It supports our life as we know it. Together, we can create a global data set of coral reefs and build a better understanding of how to save these aquatic worlds, one piece of coral at a time. Good luck, and welcome to the NASA NemoNet team.
Any NemoNet players? Don't be shy, don't be shy. No, I know there's at least 3 that have hardcore trained it. Please take extra cookies to reward yourself. And if you haven't played it already, please join the millions of people that have been logging in and trying to crash our servers and play it and just have a lot of fun. We've been working on translations of NemoNet. It's really kind of taken off as a way of classifying reefs at scale. And now when you go to our online data viewer, in addition to seeing the fluid lensing data sets for a particular region, the bathymetry products, you can also pull out some of the habitat maps and the diversity in those reefs through things like Shannon's Diversity Index and other higher level metrics. So this is still very much in a prototype stage, but I'm hoping by fall we'll have quite a lot of global products. Yes, Anna? In time for our HU fall meeting. One thing I did not mention was our new fluid lensing depth record from our 2022 campaign was 65 feet at around 5 centimeter resolution, which is a higher depth than the satellite can achieve. And we're looking to best that this year, but we haven't yet processed all the data sets from this summer, so stay tuned on that depth limit. Okay, you now might be thinking, well, 65 feet is still the photic zone. How do you get to map the rest of that habitable volume of our world, right? And explore other ocean worlds. And that's something that had been on my mind for quite some time. And in 2019, I had invented something called MIDAR, which is similar to radar and LiDAR in concept. It provides an illumination source instead of using the sun, but it does so in a slightly different way that uses multiple narrowband optical emitters. So MIDAR is really designed to look in those regions that are too dark for the sun to see, to go onto underwater robots, to go with scuba divers as a handheld platform, to go onto aircraft, and also communicate. It can send data across its optical stream. So it works using an active transmitter. This is usually just like a radar or LiDAR source, a sequence of narrowband emitters, in this case optical, so near infrared all the way to ultraviolet. They emit structured optical radiation, so that's a very unique mathematical pattern with each light sequence that's measured by a receiver, and that receiver can then decode what that optical signal color is and assign a reflectance to it. So what that means is, with MIDAR we can identify lots of emission chemistries with laser sources or LED sources, span the electromagnetic spectrum, and then illuminate objects in those wavelengths to study the object's properties. But crucially, we can do it in wavelengths that may not be produced by the sun in abundance on Earth, or are highly attenuated, because we fixed mostly the hole in the ozone layer that is permitting a lot of other ultraviolet light to come through. UV has a lot of spectral content, particularly for things in the water. When I say we need the Webb Space Telescope moment in oceanography, I'm talking about the wavelengths we look at. Hubble Space Telescope is designed to look at optical wavelengths, red, green, and blue, the things that you and I see. But we are, again, monkeys that evolved on a planet's surface that uses red, green, and blue for most of our biological needs. If you live underwater, red is useless, right? Green, slightly more useful, but in blue, there's a plethora of colors and ultraviolet that humans are not perceptive to. So just like when astronomers created the Webb Space Telescope to look at the universe in the right color, namely the infrared, where a lot of the older galaxies reside and emit because the light has been stretched by an expanding universe, when we look at the ocean, we have to think like fish. We have to think in the ultraviolet and the blue. And unsurprisingly, we're seeing a lot of data about how corals, fish species, both communicate bioluminescently in blue, have fluorescent pigments, have ultraviolet pigments, have a lot going on in wavelengths that we're just starting to appreciate even exist. So with MIDAR, my main goal for the oceans is exploring the spectrum that traditionally we've just thought of as kind of one monolithic color, but really there's a lot more going on. So you have an idea of how this works. On an aircraft, this is MIDAR slowed down so you can see the individual light pulses. It flies with a transmitter and a receiver. They can be co-located or separated. And what that aircraft can do is fly over a coral, for example, underwater, illuminate it in these different wavelengths with its special code, and then see a multispectral reflectance image of that coral. This is a Pleiades coral in Guam. And what's interesting is in red, green, and blue, it looks rather the coral. But once you start getting into the higher energy blue wavelengths towards the ultraviolet, you'll start noticing a number of unique patterns that tell you a lot more about the physiology of the coral, if it has a type of disease or not, if it's been bleached recently or not, and its species type, which in ultraviolet is a lot easier to classify than in color. So I'll share some of the new projects that were recently funded with these technologies. One is a 13-channel MIDAR unit that's designed to fly an aircraft as well as go underwater, and recently saw some whales. We actually manufactured this in-house with our CNC machines. This is Cam's very late night work CNCing this particular MIDAR heatsink. And we're deploying it on more than just corals and whales. We're also looking at the other things we're putting into the oceans, namely anthropogenic marine debris and plastics. So this is a little beach scene we gathered just right off our shore here at Rosenstiel. It's got an assortment of plastics. You can see some of them. Someone's lollipop, I don't know, cork. Lots of microplastics up here. So the challenge with plastic always is that spectrally it looks a lot like life. It looks like algae, especially when it's been in the water for a while. It gets covered in something, it gets biofouled. And then spectrally it's very hard to distinguish from a living thing. This gets even more difficult as it gets submerged underwater, because all the spectral features of plastic, which exist in the shortwave infrared, they're all absorbed in water. So to study plastic at scale, you have to again look at different wavelengths. This is a slowed down MIDAR image of that little test environment. And what you'll notice is in the blues here, in the ultraviolets, all of a sudden you start getting microplastics to both fluoresce and exhibit unique reflectance features that are different than the background. And that's the signal we are looking for to detect plastics. So it's tantalizingly in our grasp. We can start measuring macro scale plastics and micro scale biofouled plastics using this technique, but it has to be developed and deployed at scale. That usually means aircraft. So we've been flying this particular instrument. We get a lot of UFO reports, but it is not a UFO. It's very much identified through like ADS-B and everything else. This is MIDAR slowed down again, operating over a test target. Here you can see it in Guam, illuminating their plastic debris scene after Typhoon Mawar just hit. And what's exciting again, we tried to spell out ACES with plastics. Kind of blown away, but that's it right there. It's a bright signal, and there's multiple other signals within that frame that exist, again, only in those wavelengths that are imperceptible to human eyes, but are much more common in the ocean environment. So there's a lot of marine debris. I'm leaving Friday for Marine Debris Conference in collaboration with ESA and NASA, and we're hoping to advance that technology a lot further to try to get to, hopefully one day, satellite-borne plastic sensing, or at the very least airborne sensing, so we can get a handle on where these plastics are coming from, their density at sources and sinks, and try to restrain them. Another fun project that I got recently lured into by some collaborators was looking at whales with these two technologies. We just came back from last week being on this vessel with my students' custom drone launch pad system, which has earned its weight in gold because it saved a $100,000 instrument 4 times from plopping in the water. This is what most of our operations look like. This is a calm day.
Nicely done. Hot dog. Holy cow.
Yes, collaborators. To give you an idea of what these whales look like, this is the first 8K footage of very unique humpback lunge feeding behavior. We're looking at anchovies getting eaten up by these 2 big fellows. We called one Barnacle Bill, the other one had a more scientific name that was tagged. And I just processed this. What we're finding is what we were hoping for, which is we can start imaging whales underwater at high resolution, identifying them based on their unique dorsal patterns without waiting for a tail fluke, which allows us to start doing a census of these whales, and then also maturing technologies that eventually can prevent ship strikes. Most of these cetaceans in the San Francisco area are hit by large cargo container vessels going about 30 knots into the channel. You'd think a whale would be very clever and not hear this thing coming, but even if you're a human in that surface environment, acoustically the ships have a refractory acoustic wave, so basically you can't hear a giant shipping container coming at you if you're in the first like 30 meters of water and you're right in front of it. So you get struck by a very large thing, and then a lot of these whales perish. So we're trying to change that by getting an early warning system that's based on airborne surveys, which can be done rapidly under the cloud layer, which is crucial for many of these environments because satellites cannot penetrate those clouds. And then this one, we've actually been tagged with a little suction cup tag, so we can track and know its depth as we're imaging it to kind of validate the technology. So we're looking for more collaborators on this project. We have a couple of large grants from Stanford, and we'll be going back there next year with the helicopter, and I'm going to be dangling from the helicopter with that MIDAR instrument to try to get closer to these whales, which are very stubborn to cooperate with when you're trying to take a picture of them. We took some MIDAR imagery also of the whales. That's my student Cam on top of this vessel with MIDAR at night. The whales found it very interesting. This was all permitted, by the way, under the Monterey Bay National Marine Sanctuary's Common Book Bird permit. But we'll be going back with a higher intensity MIDAR to try to get a UV image of a whale, which would also be a first. All right, some of you may have seen this vessel from 2022. One of the things I wanted to do in moving from astrophysics into oceanography is trying to decarbonize the work that gets done in earth science. It's kind of remarkable that we spend so much time assessing the carbon budget, right, and how much it impacts the very organisms we care so much about. But then marine science itself, right, it's expensive and it takes a ton of carbon to do. Some things you can't get around, but we're trying to advance the state of the art every year so that we can get to the point where we can do zero carbon missions. So that Horseshoe Reef mission in Florida, that was the first completely solar powered electric coral reef survey in history. So the aircraft were electric, the boat was electric. We built this solar boat, the small one. And the tow vehicle that got us down to John Pennycamp was electric. So we had an electric truck towing this electric boat. So it can be done. It's slow, and you get a little seasick on that little vessel. I don't get seasick on bigger vessels, I believe. That was also kind of the predecessor to the new vessel that you may have seen now parked in front of Tritium, the Flying Electric Research Vessel, which just arrived here. We developed this in collaboration with Candela, a Swedish company that's also been pioneering the push for sustainable boating. One of the challenges for electric boats in general is just range, right? Just like cars. You need a lot of batteries to go somewhere fast. In boats, you need, for every 2 times the speed you want to go, you need to the third power more energy. So it's not trivial to go far in a boat and to go fast, unless you change the physics of the problem. And that's what Candela has done. They've developed an active foiling system. So under this vessel, there are 2 retractable wings that are actuated that lift the entire hull out of the water. And now the drag equation no longer applies. And this vessel can go close to 40 nautical miles. This is the vessel taking off. It takes off at about 15 knots or so. And once you're up, it's active surfaces. So there's no weight. You can fly through a wake and you're stable. There's also no wake behind you. Here you can see a little bit more of those foils. This is in Biscayne Bay. We can carry about 1,800 pounds on this particular vessel, and I've already looking at some other investments, but this is something that can be a workhorse, right? You don't have to go somewhere slow, which our last vessel was very much a slower, but semi-reliable electric boat. This thing gets you there fast, and it gets you there incredibly efficiently. To go down to Broad Key and back takes about $1 of electricity. To go to Broad Key and back on our current boats takes about 35 gallons of fuel, which at California prices was like $175. So not to mention the carbon footprint and the noise footprint and the oil emissions into the water. So we're hoping that this is kind of leading the way in building a more sustainable type of marine science. If you're curious how it lands, basically just like an aircraft, the wings will stall, it'll come down and reach touchdown. When it's on foils, it flies just like an aircraft. I'll show you what it looks like from inside the vessel.
Of course, I felt like I was a Pirates of the Caribbean.
And that vessel already has multiple grants that are going to be, it's going to be supporting for National Geographic, NASA, and most recently the DoD. So we're integrating aircraft onto it, charging systems for those aircraft, all electric aircraft, and a MIDAR array on the bow, where hopefully we can start making these measurements. Again, using this unique property of flying, we don't have any bow interference. So the view from all of our sensors mimics that of an aircraft flying over the water. So it's a great way to validate and prototype these technologies before we fly them on expensive airborne missions that have high peril of things falling in water and dying. So, I know I painted a bit of a grim picture in the beginning that we've mapped all these other celestial bodies, why is Earth been left alone? But this is changing, and I'm certainly not the only one in this field that's working on this. There's dozens of others that are pushing the frontier in terms of sustainability and getting into all the different layers of the ocean. And so it's changing. Since this talk is focused very much on my promotion capability here, I want to draw attention to the extramural funding record. So I presented this when I first got here up till 2020. I guess since moving to Rosenstiel, I've gotten very lucky with proposals, and we've won 100% of the dozen plus proposals submitted from here, which I will attest to the faculty cajoling me into writing better proposals, and some of my collaborators. I had the opportunity to work with Professor Claire Paris, Sam Perkis, Art Gleason, a number of folks that are really the reason that brought me to Rosenstiel. Since I've gotten here, I've raised about $6 million of extramural funding, and knock on wood, this trend continues. We can, in next year, hopefully secure some of these larger multi-million-dollar grants that will propel us into an exciting future. So there are 7 new proposals in review, and we also secured it was going to be $2.5 million drone center commitment from Congress. Now it's down to $1.3 million due to Congress. But we will be developing a new drone center here in-house and building some of these sustainable aircraft. This was a high-altitude solar drone that I developed at NASA, and we'll be 3D printing our own versions of these things here soon, and then flying them with sensors that everybody, if you have an idea of what you need to do a long-term mission mapping sargassum or something else, please come to us, tell us your requirements. Let's start working together and using aircraft more and more. We're going to be developing this system on the flying boat with a smaller aircraft. So we'll be launching the aircraft from the boat once it's reached flight speed. It's perfect for these longer wingspan aircraft to take off, and then they water land when they come down. So hopefully in the next couple of years, you'll see that new development occurring right here at the dock, and then in Key Biscayne, which used to be quite popular with seaplanes coming and going. So I'm hoping that returns. Looking towards the future, I have a project with National Geographic in review called Project Cerulean, and we would massively expand the footprint of fluid lensing capacity building to 5 ocean basins in 6 new countries. This is something that I could only do from a university position. It was very difficult to do within the government because of how we fund things only domestically, but that's okay. With National Geographic, we're hoping to expand the reach of that technology and then basically map as many corals as we can with as many international partners as possible. If you're interested in learning anything more, especially on the technical side about this work, I encourage you to check out a new series in oceanography called Oceans Across the Solar System. I led the publication of a number of technical papers there that are hopefully going to be motivating a lot more space-focused work on Earth's oceans. And with that comes aerospace levels of funding, where you add a few zeros to your budgets. That's typically what we use in aerospace. For students, I have a new course that I've been writing a textbook for with my colleague Sam Perkis. This will be offered next spring. It's a 4-unit course on planetary science, the search for life, and oceans across the solar system. If you want to take a ride on that flying boat, sign up for this course. It is limited to 20 people. You have to be able to swim and be good at maths. But other than that, everyone's welcome to join, and I hope that we can start up a larger planetary science community here with the oceanography expertise we have. That's sorely needed. In 2024, I will also advertise 3 new PhD fellowships. A couple of these will support Project Cerulean. Another couple are for NASA grants, National Geographic grants, NSF grants, and a DoD grant that will go primarily into MIDAR and FluidChem. So if you're nearing graduation timeline, please visit the Rosenstiel website or the ACES website to learn more about these fellowships. I'll also very soon be advertising 2 staff positions in my lab. These are full-time positions for after you've graduated. So you can apply to these if you're interested as well, and they'll be posted on the ACES website. So with that, I thank you for your time, and I would be happy to take any questions.
Yeah.
Yeah, John, how about you go first? Since you
Yeah.
arrived first.
Okay, thank you very much for a great presentation. Dynamite. I've been out on vessels at night, and I've seen bioluminescent coatings on dolphins and things like that. They tend to be sheathed in bioluminescence. It'd be a neat target for some of your observing systems.
Yes, I've seen that video, John. It's quite exciting. In fact, I just downloaded, my colleague sent me a paper. Koalas and a ton of terrestrial mammals apparently also have UV fluorescence that we're just learning for the first time. Flying squirrels are like wild in the ultraviolet. So that's something we will definitely look at. There were dolphins in abundance in Monterey, so we're hoping to capture some. They're a little bit, more finicky to image than whales. Whales at least don't move as fast. So
Yeah.
Amy.
Thanks, Ved. Super interesting stuff. I'm really taken by your idea of the James Webb for the ocean, and I'm curious, what drives like that, was like the search for exoplanets, or what if we did that? What would you hope to discover? What would be the science driver that would, that you could convince us that we should spend $7 billion on it, besides the fact that, there's a gap?
Yeah, well, I mean, the congressional pitch for James Webb in Congress was not well received in that it was very dense, right? Astronomers were talking about early expansion of the universe, primordial quarks, things that are,
but all great science questions.
Great science question. I feel we have an edge, right? For one thing, all the voters live here. They don't live at Lagrange Point 2 or in the outer cosmos. All of the things that are happening in our biosphere are occurring in the water. And there are missions like PACE that has recently been funded by Congress that are billion-dollar flagship NASA oceanography missions that are looking at ocean color, but we need more. Back in the early 60s, NASA funded something called the Sustained Land Imaging Program, and that is what gave birth to Landsat in its 9th iteration. That's a multi-billion-dollar a year investment in studying terrestrial change. And we need a sustained marine imaging program, and it cannot just be a satellite system alone. It will likely need to be, just like SLI is, the Sustained Land Imaging Program, a combination of satellite assets, airborne assets, in-water assets, or terrestrial assets in the case of SLI. Things like Argo floats that are just profiling the column, basically getting a census of the biodiversity of the oceans at scale, at all depths. And that's, you can't rely on any one technology to answer that. So what I'm hoping is that there will be, I'm certainly pushing, now that I'm outside of the government, I can push on Congress to say, hey, we need a sustained marine imaging program. The majority of our surface of our planet is aquatic, and our livelihood depends on it. Everything from climate change to fish protein to shore protection to medicines, right? All of that's coming out of the sea. So we need an investment that is 4 times the size of James Webb, at least, because James Webb is studying something that is still quite small compared to what we experience on Earth. Does that answer your
Well,
question?
kind of, but I still want to push to say, so let's say you're not trying to convince Congress, but you're trying to convince the scientific community. What are we going to learn?
Oh, what are we going to learn? Okay, so the first is just our origin story, right? It's the same questions that astronomy is trying to answer. We now think that life originated in hydrothermal sea vents, and they're the most poorly surveyed biosphere around. We have very little data on where they are, the abundance of life in it, and the diversity they contain. They have not been genetically sequenced. Many of the organisms are going extinct on our watch, and the trouble is that those organisms have evolved things like advanced biomedical solutions to problems like COVID. That, the last COVID drug came out of a coral reef that was 30 times more effective than remdesivir. But if that coral reef had gone extinct, or that species had gone extinct from that reef, and we didn't survey or understand how it worked, then we lost out on free evolutionary advice on how to battle something like COVID. I think the same thing exists in the deep sea in particular. There are entire environments that have not been well captured or surveyed, and so we don't really have a good grasp of the tree of life because we've been blinded by the tree, right? We're monkeys from a tree. We should be thinking about the Medusa of life or something a little more oceanic based. And so that fundamental knowledge is lacking. I think the way we've done it on land to survey large ecosystems at scale is through multispectral remote sensing. That gives you huge synoptic surveys of the environment, It allows you to assess ecological change, ecological significance, and do so without touching the environment or having to invest tons and tons of resources in visiting each rainforest. That's what informed the national park boundary, was the first Landsat pictures of land, and then looking at boundaries where human settlements were agricultural fields and saying, okay, let's protect this key biodiversity area. Right now in the ocean, it's kind of limited to, well, this is what we can see from the top. It's a few coral reefs here and there, we should protect those. But what if we've got it wrong? What if the majority, and a lot of those reefs are mesophotic or deep sea corals? Those might be more important ecologically to protect or to understand than the shallows. But we don't know that fundamental question until we've done that survey. So it's, kind of a fundamental knowledge, I think.
Thank you, Dave. I have a question about NEMO. It seems like this is a really cool citizen science opportunity. Is there a plan to build a curriculum around it so they can implement it in public schools?
Yes, there were 2 Einstein Fellows at headquarters at NASA that were doing exactly that, building curricula to teach at K through 12 level. I believe, Anna, you did a survey, we worked with some educators on NEMONet materials. We typically go to schools with NEMONet and get kids to kind of play, and they learn, it's kind of a built-in curriculum, right? They get taught what coral looks like of different types. They learn that they can't really cheat, that we're measuring everything. And so, and our last effort is with NOAA, we're trying to operationalize NEMONet, so it's adopted in all of their survey methodologies and they kind of own it. But they're also looking at trying to create curricula based on the app to educate the public. For a lot of folks, half of it was, it was the pandemic and people wanted something to do. They still do that. It's very relaxing to 3D color in a coral reef. And then just like national parks where you can walk in and kind of experience something, a lot of folks either they have access issues or it's a really wealthy opportunity to be able to go visit a coral reef, right? They can do that in the game with a very low barrier for entry, and that's been something we've seen. People just are curious about the organisms. They want to see what it looks like, and so they just go in and tool around and look, and that's great. That means that person is now thinking about a coral reef like a rainforest, right?
Thank you.
Mm-hmm.
Really great talk. I was wondering, the MIDAR, how deep can it go now? And then if you're looking at the deep ocean in the future, are you hoping to attach it to robotics and then have it observe the deep floor that way? What's the future?
Yes, you should come to that class, I think. Well, I could. So right now, MIDAR is not very powerful. The sun produces about 1,300 watts per square meter at all wavelengths that are visible. MIDAR produces, I'd say, about 4 watts cam per square meter, 5 watts at a range of 25 meters.
Yeah.
Okay.
Sometimes we get up to maybe 20 watts in certain wavelengths.
It's like the early days of radar, right? The first radars, no one was comfortable putting a megawatt transmitter on anything. Now you have maritime radars, which, by the way, never stand in front of because they have 14 kilowatts of microwave radiation that are zapping you. So if you get a bit warm, that's why. MIDAR, what we're trying to do is get to the solar illumination threshold. So if we get to 1,400 watts per square meter, we know that animals can tolerate that because they're around during the noonday, right? So we're trying to match that level of downwelling irradiance, is what we call it, so to get the equivalent level of signal. In the ultraviolet, we can produce more light than the sun on Earth's surface just because of the atmosphere attenuating so much and we're closer, and water removes a lot of the harmful UV, so you're left with just interesting signal. So we'll see. My goal is to try to exceed the photic zone with MIDAR through a combination of methods. And then for the deep sea, there's a few things you can do. The best is a robot. You put MIDAR on a robot, a fleet of robots that are doing multispectral deep sea surveys, right? So an armada of little flying gliders that are surveying the seafloor just like we survey land with spacecraft. We just have to think of space as, water is also space. It's quite empty, but some of it is not, right? So we should deploy systems like that. Or right now, what we're going to be doing is sticking it on some divers and giving them a handheld MIDAR unit to go up and image objects for us. Divers are much more reliable robots. So, yeah. Mm-hmm. Any other questions? And then long term, just to motivate some thoughts, because I'm writing this textbook, there's in astronomy, we don't, it's kind of a nice field because you're limited in what you can work with, and what you can work with is light, right? That's the only thing that really travels across the universe. Sound waves you can see in other nebulas, but you can't hear them, you can't touch them. Other things that travel through the universe are neutrinos, with very little collisions, and gravity waves. And we've gotten quite good at detecting large gravity wave events where two black holes collide and merge and shed gravitational wave energy. One of the chapters I'm writing is on the potential of gravity wave detection for seafloor mapping and detection of what's in the column of water. There's a lot of work that's been going on with GRACE, FO, which is GRACE follow-on, not the other thing, which is a NASA mission that measures gravity perturbations on the surface of the Earth. And what they've actually been able to do is look at the deficit in aquifers above states by the deficit in gravity for that state and infer the total amount of water that's been pumped out. The technology is advancing quickly, and I think that one day, we've got to start thinking about mapping the oceans in not just new wavelengths, but entirely new methods. Neutrino-based, meson-based scanning, tomography, or gravitational wave detection. The deep sea actually isn't even dark. It's got Cherenkov radiation that comes from the decay of calcium, radioactive calcium ions. So when you go down the deep environment and everyone says, oh, it's dark, well, like all the particle physicists put these giant arrays up to detect neutrinos, thinking, great, we found this perfectly dark, at the bottom of the ocean, water scattering medium, and instead they had half their signal was bioluminescent fish doing who knows what, and the other half were Cherenkov radiation from radioactive particles that are in the entire column. So there is a background level of light, and whenever astronomers hear that there's a background of something, they're like, oh, I can detect something against the background. And that's kind of what I'm hoping to do for, 5 years down the line, 10 years down the line, gravimetry or neutrino-based detection of things.
Yeah, hi. I have one more question. If you're going to survey the vents, the deep sea vents that mostly occur in spreading centers, it might be an interesting thing to figure out how to generate electric power out of the temperature difference across the vents as a recharge mechanism, and then you could have a long distance mission going from one spreading center vents complex to the next, essentially flying down the mid-ocean ridge.
That's a great idea, John. Yeah, John's referring to if you use the thermoelectric effect to exploit a temperature differential across like a Peltier device, then you can generate electrical current. We use that to power deep space missions using a nuclear generator. But you could also use a hydrothermal vent for that purpose if you had a cold source next to you. So yeah, that's a good idea, John. I'll have to I'll tell NASA, hey, don't forget this idea.
Okay, thank you.
In your talk, you have been mostly or only talking about optical or electromagnetic waves. How about sonar waves?
Yes, again, as an astronomer, I'm kind of biased towards the electromagnetic spectrum because it's nicely quantifiable. Sonar has amazing advances, and I think any sustained marine imaging system equally would use a sonar component to do a lot of the mapping. Most of the seafloor mapping has been done with active sonar in these deep sea environments, but for me, it's the optical side of things has a larger frequency range to work with. And so I'm more attracted to that, and I understand the sensors on the optical side a little bit better than the acoustic sensors. But that's not to say I'm shy away from an acoustic collaboration on a...
The problem is that optical waves, they have very limited range in water. You're not in space, in vacuum, and actually much more suitable for exploring or mapping inside water would be acoustic sonar waves. So if you talk about efficient mapping with low energy, also you said about moving robots close to the deep sea, you need a lot of energy. In space, you can move sensors like without any energy requirement. It just moves by itself, the satellite. You don't need to have propulsion.
Well, I mean, rockets would beg to differ, but in the acoustic regime, the challenge is, in general, there's a physical scaling law. The more energy a particle has, or waveform it has, the more energy content is inside of it. So with electromagnetic waves, when you get spectral features, polarization states, these provide a lot more information about the object you're looking at than acoustic systems, which is why even in these shallow reef environments, we have won all the proposals from our acoustic competitors, because when they give an acoustic image of a coral reef, the biologists say, I don't know what that is, right? Rugosity alone cannot tell me the coral species. It cannot tell me if it's suffering from a disease. It only tells me the acoustic reflectance of that particular object. So right now, what optical allows, at least in the regions where it has limited range, right, your photic zone, it gives you that scaling law that physics says the more energy this particle has, or this acoustic or electromagnetic wave has, the more information can be gleaned from it. And that's something that, you know, although oceans don't do well in the radio wavelengths or optical visible wavelengths, they actually do transmit again in ultraviolet, in X-ray, and gamma. And those are things that I think should be more exploited. So I don't think the story's completely closed on optical sensing of the seas having limited range. I think there's a lot more to explore there. We just started getting into that environment. Is that something I can?
Yeah, but it might be still, when you want to do your optical mapping, it's high, like you say, it's very high resolution, you get a lot of information, but like with every exploration, you need to know where you're going. And then it might be very advantageous and efficient if you have an initial picture of the site or the area you're going to explore.
I agree, and we work a lot with acoustic partners on trying to pinpoint, you know, mapping areas and protocols. But you know, the same could be argued for surveying Earth, right? You can send a satellite up to do it, and it costs a lot of money and rocket fuel. You can also just send a balloon up and just wait. Right, and the balloon will eventually circle the planet multiple times and survey most of what you want to see for free with very little fuel. But there's an opportunity cost, right? Sometimes you want to go somewhere. Sometimes you don't want your balloon to be shot down. Sometimes you don't want your satellite to cost so much money, right? So there's this trade space, I think, exists for the ocean, and that's kind of the realm in which we're all living, right? Can we figure out the right mixture of acoustic, optical, future gravimetric-based sensing that allows us to survey the full biodiversity of life? Cool. All right. That's it then. Well, thank you all again. Please enjoy some biscuits.